All right, we're continuing with the curve sketching example problems. This is video number 13. In this video, we're going to sketch this function shown here, e to the 2x minus e to the x. All right, step one, the domain. What is the domain of e to the x? You can input anything you want into e to the x, and so it's the same idea with e to the 2x. So the domain here is going to be all real numbers. Okay, the range should also be all real numbers, but we'll come back to the range later in the video. Okay, intercepts, y-intercepts. Let's set x equal to 0 and solve for y. So we get 1 minus 1, 0. Okay, so the origin is an intercept. It's going to be an x and a y intercept. What about the y or the x intercepts? That was the y intercepts. Now let's set y equal to 0 and solve for x to get x intercepts. Okay, so e to the 2x minus e to the x. Okay, so we set that equal to e. Now let's solve for when that equation e is equal to 0 for x. X is equal to 0, so x is equal to 0 is the only intercept, x or y. Okay, so we're going to go from minus 5 to 5 on the x and the y. Okay, and the origin is the only intercept, x or y. Okay, now let's check for symmetry. Is this an even function? So we look at y to the minus x. Okay, so what we do is put minus there, e to the minus 2x minus e to the minus x. This is not equal to the original function. Okay, what about an odd function, so that we would get e to the 2x plus e to the x. This is not equal to y of minus x, so we don't have an even or an odd function. What about periodic symmetry? Is there some number p such that y of x plus p is equal to y of x? No, this is not a, we're dealing with all the typical types of functions that we've learned in algebra and trigonometry. This is not one of the ones that we know that could be periodic, like a trigonometric type function or a hyperbolic function. It's not involving any of those. Okay, endpoint behavior. Let's take the limit as x approaches each of the endpoints of the function. So what is the limit as x approaches negative infinity of the function? So, okay. The limit as x approaches negative infinity of the function is 0. Okay, what is the limit as x approaches positive infinity of the function? Okay, it's infinity. All right, so we're going to have a horizontal asymptote as x goes to negative infinity. It's going to be y is equal to 0. So the function's going to be doing something like this. Okay, and then as x goes to infinity, the function goes to infinity, so it's just going to be coming off like that. All right, next, let's get critical points, both with respect to the first and second derivative. Let's start with the first derivative. Okay, so we've got d dx. Okay, that exists everywhere, but where, let's solve for where this equals 0. Minus natural log of 2. Okay, and that's it. Again, this exists. There's nowhere where this won't exist. Okay, so all right. What is minus natural log of 2? Is that is a negative number? Because I know like logarithms are. Yeah. Okay, so what point is this? This is minus natural log of 2, and then if we put into the function, so e with x equal to minus natural log of 2, minus 1/4. Okay, all right, so now the second derivative. Okay, so all right, now let's solve. That exists everywhere, but where does this equal 0? Solve for when this equals 0 for x minus 2 natural log of 2. Okay, so minus 2 natural log of 2. What point is this? E with x is equal to minus 2 times natural log of 2, minus 3/16. Okay, now let's plot these points. All right, minus natural log of 2 is what? Minus 0.69, and then minus 1/4. So minus 0.69 minus 1/4. Minus 0.69 is about right here, and then minus 1/4 is about right in there. Okay. Okay, what is minus 2 natural log of 2? That is, okay, minus 1.39, and then what is 3/16? Okay, minus 1.39 minus 0.19. Minus 1.39 about in here, and then minus 0.19, so like about right there. Okay, now let's get the increasing, decreasing intervals. So okay, minus natural log of 2 was what? Minus 0.69. So, okay, we've got 0 and then minus natural log of 2. And so we can only change signs across a critical point. So, all right. Let's take the derivative with respect to x of e. Let's take the derivative with respect to x. Okay, so this with x is equal to, let's do minus 5. Okay, so this would be decreasing. All right, now let's do this with x is equal to 0. Increasing. Okay. So we've got here is going to be a local min. We go from decreasing to increasing. This function is continuous everywhere. So yeah. Okay. Now let's do, so 0 minus 2 natural log of 2. Okay, same process here. So take the second derivative with x equal to minus 5, let's say. Concave down. All right. Now, let's just do x is equal to 0. Concave up. Okay, so this is going to be an inflection point. The function's continuous everywhere, and the second derivative changes signs here. It's not going to change signs anywhere else other than these critical points. The first derivative can only change signs across a critical point with respect to the first derivative, and the same idea with the second derivative. Okay, now let's draw the curve. So what's going to happen is here the slope is equal to 0, so we're going to do like that, and then we'll come concave up here and then switch to concave down and then approach 0 like that. So we're concave up to here, and then we switch to concave down. Like that. I mean, perhaps I should have zoomed in more, but that's the idea. So as x approaches negative infinity, the function approaches 0. As x approaches positive infinity, the function approaches positive infinity. We've got the function is decreasing all the way until this point here, which would be the local min, right? It's decreasing all the way to there, and then it's increasing for the rest of the time. Yep. Right? It should be concave down all the way to this inflection point. Then it switches to concave up for the rest of the function, right? It's concave down, then switches to concave up. There's only one x-intercept and only one y-intercept. So there you go. All right, now, what is the range? Okay, well, we can see the range is going to be, if we come to this local min here, it's going to be minus 1/4, including the minus 1/4, to infinity, right? We cannot, there's nothing we can input into this function and get like minus 4. Nothing. We can only get from minus 1/4 to infinity. Okay, and that's the graph.